it's a pleasure for me to introduce our invited speaker, Professor Dariusz Dereniowski. Darek is working in Gdańsk Tech by former university, but we were working in the same university but different departments. Darek is working at Faculty of Electronics, Telecommunications and Informatics, but he's both mathematician and computer scientist. His research interest covers a wide range of theoretical computer science, including graph theory, algorithm, operation research, and mobile agent computing. For me, Darek was always an expert from algorithm and complexity problems. And recently, he is interested in restate the classical binary search in a linear order to more general structures, particularly for graphs. And in his talk, he's going to give us an introduction to these problems and discuss them from the structural and algorithmic perspective. Everybody's talk about some story and relations with invited speakers, but in case of Darek, sorry, I have closer relations to your wife, because Darek always brings his wife to the conferences, and we spend all the social events together. So I can ask you to send regards to Gosia, and Darek is going to present us a talk about searching in graphs and related problems. So Darek, please, the floor is yours.
Okay, okay, thanks a lot. So are the slides well visible? Is it okay this way?
Yes, it's okay, it's visible.
Okay, good. Okay, so the idea for this talk is to not to go into too difficult stuff, and rather present a whole variety of problems with some basic maybe tricks or connections between them. So for this reason, I mean, I want to tell a story where we will having certain graph searching problem, and I will try to convince you that this problem is kind of natural for computer science, for algorithms, and also for structural problems, because it reappeared several times in different areas under different names. In some cases, different groups didn't even know that other formulations already existed. So this is kind of an argument that the problem seems to be natural. It captures some kind of bisection in a graph theoretic context. And hopefully we can all relate to the fact that we will be generalizing the classical binary search in a sorted table. And I will make this connection at some point. I'm also depending where you are, it's kind of late. So even if you lose a part of the lectures, there will be a chance to get back on board, because I will restart a different formulation of the same problem. So hopefully we will get some kind of understanding of all this. So I will start with something that was studied a long time ago, I suppose in the 70s, and it was used under a name of elimination trees. And the way I encountered the problem, it was in the context of some kind of parallel matrix factorization. So it seems unrelated, but let's have a look at definition. I will not go into the applications. I will mention some applications, but not this one. I mean, this matrix stuff would be too time consuming. So suppose, in this talk, we'll mostly work on trees, although most of this stuff generalizes to arbitrary graph. In particular, the elimination orderings do. So suppose we have a graph and we take any permutation of vertices and we create so-called field graph by repeating the following process. For each vertex, we do a certain things, which is usually called like eliminating a vertex. So what we do is that when we pick another vertex, say pi, then all the neighbors of this pi which have not been eliminated yet will be made into a clique. So we are adding edges. We never remove anything. We're adding edges. So the later we are in the permutation, the smaller the chance that we will be adding more edges. For example, like the last two vertices never contribute to adding anything when we eliminate the last two. Okay, so we have this field graph, and I will do an example. So say we have this. Maybe I will do this. So I took a tree and took just any permutation of it. I took tree because I don't want to have too many edges, just for that. So when we eliminate the first three, in this case, like the first three leaves, then nothing happens. But when we eliminate P4, then we add this edge between P11 and P9 because they are later in the permutation and they are both neighbors of P4. So they are supposed to make a clique now. P5 doesn't do anything. P6 will add another edge. And we can see that although it seemed at the beginning like very far away vertices, like P10 and P11 didn't seem to become neighbors at any point, but they will. Because of these two edges that we've added in the meantime. So now we eliminate P9 and therefore this new edge. So, okay, so we have this kind of graph, and based on that, we want to create a tree. So this will be always a tree. So the product of our, so we are still like in the problem formulation. So the product of all this will be to create a certain tree. Even if the input graph is not a tree, we want to formulate tree, therefore the name elimination tree. And the rule is that the parent of pi is a vertex which was, first of all, it must be a neighbor of pi in this field graph. And also, if it has many neighbors, then we'll pick the first one according to the permutation. Okay, and this way we are creating, so going back to our example, this kind of creates a parent-child relation on the vertices. This creates a tree. And what we want to have here is that we want to find an ordering that will give a tree of minimum height. So that's our that's the optimization criterion. I mean, there may be others, but that will be the one that corresponds to the search time in the like binary search problem. Okay, so now we will leave this problem aside for a minute, and we will jump to another problem on which I work from time to time. It's called it is a certain coloring problem. It is called vertex ranking, but it has also other names like ordered coloring also was used sometimes. So the definition is that we assign colors to vertices, and whenever two vertices have the same color, then each path between these two needs to have a vertex with a higher color. So unlike with typical coloring, like when Hannah was talking, we are mostly interested in comparing colors whether they are the same or different. But here we have some kind of ordering on the colors. Like we want to compare that some colors should be higher than the others. Okay, and the goal is to find a coloring of the sort that will be minimizing the number of colors. So just to have some intuition, like this coloring has some maybe strange properties at first. Like the obvious thing is that a coloring always exists. We can give different color to each vertex, and this is okay with respect to this definition. Also, a property that is like very useful and will play its part in a moment is that the vertex that has the highest color is unique in this coloring. Because we cannot have two, because then there is a contradiction. I mean, there is a path between them, and this path should have a higher color. So the highest color is always unique. Okay. So just to have an example, I took the tree from the last time, and this is an example of a coloring. Actually, this one is optimal. Like two colors are not enough. And also it is quite often what is maybe difficult to capture at the beginning is that if we have a repetition of color 2, so we have two 2s, then that does not mean that everybody on the path between them has to have higher color. It's just one is enough. One separating higher color vertex is enough. In this case, we have 3. Okay, good. So now, like, they seem to have completely different definitions, the two problems, but like surprisingly, they are exactly the same problems. And maybe like a short intuition why that is. So basically, we would argue both ways, like the minimum height elimination ordering is less than or equal to the number of colors and vice versa. So when we start with ranking, I would say this gives us permutation. And we do the permutation in the following way. Like first we schedule all vertices with color 1, then 2, then 3, and so on. So the higher color, the later in the permutation the vertex is. And so let's do that. And the idea is that the height of the elimination tree, because there were 3 colors in the ranking, we expect, if the proof works, to have an elimination tree with 3 levels. And it kind of comes from like induction. Like what? Why do we have the? What's the best way to put it? So is it possible that we have 2 colors, number 2, for example, and what should happen that they should be related in the elimination tree? According to the definition, they would have to be neighbors after we do the elimination of all the vertices. But how this can happen that 2 vertices of the same color become neighbors? Well, we would have to eliminate everybody on the path between them gradually, one by one, in some order. We don't know in which order, but we would have to eliminate the vertices between them. But then comes the contradiction, because in the coloring there is one vertex that is of higher color, which will be eliminated later. So in this example, we can see that if we have 2 and 2, then there is 3 between them. So this prevents them from becoming neighbors. And because this works for any label, like we can we obtain that the corresponding elimination tree has each color forms a different level, like roughly. Okay, so these are 2 names, and just to say a bit more, because from that point on I will switch to trees specifically, because for trees it will be easier for us to see that we are really close to binary search. But for general graphs, these 2 formulations are not the only ones. There is another well-known parameter called tree depth. So this is exactly the same. Then there is something called lithosearch, which is exactly the same, and perhaps more. I mean, at some point I've counted like 10 different formulations of this thing. So these are two problems. Let's switch to something slightly different. We will not be looking at general graphs, but for line graphs of trees, say. So a bit more specific. So instead of looking at line graphs, we can more naturally say that we will be coloring edges now of a tree. And the rule is the same. If 2 edges have the same color, then some edge between them needs to have a higher color. So one solution could look like this. We can argue that this one is also optimal because, for example, we have at vertex C, we have a star with 3 colors, with 3 edges. So it has to use colors 1, 2, 3. At vertex K, we have also such star. So also 1, 2, 3 needs to be present. So we already have 2 trees spread it apart. So there must be a 4 between them. So like that's a short argument that 4 colors are necessary, and it worked out to use 4 colors only here. And we will try to see like what this kind of formulation is equivalent to. One way to look at the problem, because just to give some intuition, like what this problem can be seen like. It can be seen as a certain bottom-up process along our tree, which I will show in a moment, or like top-down recursive decision tree. Okay, so the bottom-up process is like this. Suppose that we want to play a game, or maybe it's not really a game, it's another formulation of this problem, an equivalent. Suppose we want to contract our tree into a single vertex, and we do it in rounds. And each round I can pick any matching, and I contract all edges of this matching. By contracting, I mean I remove the edge and identify the endpoints. So I kind of so after, if I pick this matching, and it's not a coincidence that I picked all edges of color 1, because this coloring that I just produced is helping me to win this matching contraction game. So I pick the matching, I make contraction, and I repeat the process. And the goal is to contract the whole tree into a single vertex with as few rounds as possible. So this process kind of represents some kind of assembly, database, merging process, things like that when we mean particular applications. So then in the second round, I would contract edges of color 2 and then edges of color 3. And the question may now come, how come this will work? Like if I take any tree, any edge ranking, and I follow this scheme, how am I certain that I will really contract the graph according to the rules with the number of steps being the number of colors? And the answer is that of this tricky property of this coloring, like what can go wrong with this contraction game? Well, the only thing that can go wrong is that at certain point, like maybe now, I would try to pick a matching that I would try to pick a set of edges that is not a matching, meaning that I will pick two edges and they are adjacent. And the answer is that this is not possible because they have the same color, and so say 3 in this case. And the history of my behavior in this contraction game is that I already contracted only edges of smaller colors. So if I would create a situation that two edges with color I come together after I minus 1 steps, that means that contracting edges of color 1, 2, 3 up to I minus 1 brought edges of color I together. But that would mean that on the path between them, all the contraction path didn't have an edge of higher color. So that means that such a thing should not happen. In this picture, if 3 and 3 were together, that would mean that I contracted ones, I contracted twos, and now two threes are adjacent. So that means that there was a path between them that had only colors 1 and 2, and this violates the definition. So this kind of matching game is exactly edge ranking in case of trees. Now I will not talk about algorithms because even for trees that takes a certain effort to figure out an algorithm. I don't even believe that this is very obvious that whether this is polynomial or not, but it turns out that this is polynomial. And there was a series of papers that were improving the complexity, like from n over n cubed, something around n squared. And now we know that this, if we have an input tree and we want to find its edge ranking or elimination ordering or this contraction game, or all the same stuff, then this can be done in linear time. This is basically a bottom-up dynamic programming with some tricky data structures to beat the complexity down. And now let's move to this promised partial orders. So yeah, it's a good opportunity to like start focusing because we have something new, and what we will want to get to is to see that this problem is again the same thing as our edge ranking from a minute ago. So the fun part about it is that this problem was like separately formulated independently of the algorithms that I've just mentioned. And there was another series of papers which was basically eventually getting to the same complexity for trees. Because historically, this problem was heavily studied for trees, not only in terms of complexity, but also generalizations and different criteria. So only recently there are some generalizations to arbitrary graphs in terms of binary search, at least, because yeah. So let's look at the search problem. So we have our partial order. About the Hasse diagram, we may think of it as a tree again, because we will be assuming that our partial order has the maximum element. So basically, this order will be represented by a rooted tree. There are some works on more general stuff, but let's stick with that. And the goal of our game is to find a hidden element. It's sort of, and this really generalizes binary search in a table. It's like in the table also. We want, except that we're having a linear order, we want that we know that the element we are looking for is somewhere in the table, but we don't know where. And we can get some information by making queries or comparisons of the following form. T is the target, right? And R is the relation, the order, and V is a vertex that we pick, which corresponds to the position in the table in the binary search. We pick a certain position and we check if the target is less than the value of the element at this position or greater than this element. So here the same thing. We pick a position, which is a vertex now, and we check if the target is less than or equal to this vertex or not. In terms of the answers, we can get yes or no. Yes, like graphically, would mean that the target is in the subtree rooted at V. It's less than or equal to V. So it's somewhere, it's a descendant of V or V itself. If the answer is no, then we know that the target is not there. It is not V and it is not below V. So it's in the complement. So we have exactly the binary bisection. And if the partial order has the special case that this is linear order, so our tree would be a path and our comparisons would be exactly like binary search comparisons. So if we are having a path, this is exactly the binary search problem with the classical log n search time. Okay, and like for this reason, like if we take a path and if we want to find an edge ranking of a path, then as expected, log n is exactly the optimal number of colors because it is supposed to be the optimal number of queries. So we want to minimize the number of queries. I'm a bit ahead of myself because I already connected it with edge ranking. So here is a more complicated example than a path. So suppose we have this edge ranking, again, like in this case, 5 colors. So just a quick look if it's okay. Like we have 2 4s and good, they are separated by a 5. If we take any pair of 3s, then indeed they are separated by 4 or 5 or both, but we don't need both. So this is correct. I mean, let's don't care if it's optimal or not. And so I said in the title that this is an example of a search strategy, but so far this is an edge ranking. And the tree, just to be sure we are on the same page, the tree represents the partial order. And just to be sure that we have understanding, so if we take any edge, say 2 endpoints of 5, then this Hasse diagram representation means that the lower endpoint of 5 is less than equal the root of the tree, and so on and so on. This is the same for every edge. Okay, so what we want to do is we want to use these numbers to construct a search strategy. And it turns out that they are the same. Even in the literature, sometimes it is useful to represent such strategies via such labelings. And the way we will do it will also reveal a proof that the minimum number of colors is really the worst case number of queries that we will have. So how do I do it? Just the proof or the construction is by induction. Just we recall the fact that in edge ranking there is just one unique edge with the highest color, in this case 5. So good. I will take the low endpoint of 5 and I will query it. Okay. If the answer is yes, then I'm left with this part of the graph. Because I just learned that the target is less than equal to this queried vertex. If the answer would be no, the proof works in the same way. In that case, it's just for the different subtree. But what is important is that each of those two subtrees, depending on the yes or no answer, there is no color 5 anymore. So by induction, we can say, okay, now the highest color is 4 or less. Therefore, by the inductive assumption, 4 colors will be enough to use this thing to construct a strategy. And we, just to finish the example, we follow in the same way. We just pick the lower endpoint of 4, and we partition our tree into 2 subtrees, each having 3 colors. And again, 3 is unique, because if it wasn't, then there would be a path between 2 such edges with no bigger color. So 3 is unique, and we just continue. So if we query this middle vertex by the end, if the answer is no, then we have the target. That's the target. If the answer is yes, then we would still need 1 extra query, but we have the budget for it because the color 1 accounts for it. So in the same way, in the terminology of searching in partial orders, there was another series of papers which also produced, like in the edge ranking, like they are the same problems. Just these guys were like decade later with respect to edge ranking solutions. Yeah. Okay, so what is, I still have a few minutes, I suppose, because I'm aiming at 45 minutes. I just forgot to mention, it's kind of late to say it, but if there are any questions, you can just feel free to interrupt. I will say that there is a whole bunch of generalizations. One of them, which we worked on, like because the takeaway from it is that, okay, this problem was redefined a whole bunch of times. Half of these reformulations are equivalent not only for trees, for general graphs as well. Some of them are equivalent only for trees, like this partial orders search. This doesn't have like good equivalence to our coloring problem for general partial orders than those trees that we looked at. And there is lots of generalizations or variations which seem to be interesting. One of them on which we worked on was to look what happens if we have different query times. So far, one color meant making a query which was of unit duration. Like each comparison takes the same time. But we may have a situation, and it actually surfaced in some applications of this thing, that we may have a situation where different queries have different time. Like some comparisons are quick, some are slow, and then we want to minimize not the number of queries in the worst case, but the worst case strategy length, where the length is defined as the sum of the durations of the queries that lead to a given target. Well, it turns out that this is hard. Like that, the uniform queries problem was polynomial, even linear time. This one is NP hard. There is a series of papers on this one. So then there was a series of papers with which try to build an approximation algorithm with some kind of approximation ratio. So there was several papers, and it seems that we got stuck with the square root of log n approximation in polynomial time. And so that would be a very interesting thing to the community if someone could come up with a better approximation factor for this one. And there is a strong intuition that probably constant factor approximation should be achievable. We looked at several subcases of trees, which are still kind of general enough, like bounded weights or monotonic weights, and they do admit constant factor approximation, but the general weights we still don't know. So that would be one of the open questions that I would like to put there if someone is interested. So just to finish off, like there is other equivalent formulations. Both 3depth and LIFO search are the same problems as ours for general graphs, not only trees. Maybe I don't have it. Okay. Okay. So then there are some papers which aim at different optimization criteria. So we were interested only in the worst case strategy length. But it's like in scheduling theory, not the Cmax is one option and the sum of CJs is another option. So we may look at average cost, which would be defined as imagine that sum up the search times, assuming that each subsequent vertex is the target. So what is the search time if the first vertex is the target? What's the search time if the second one is the target, and so on and so on? And the summation of this would be the average time. So it's the sum of the times of the search. Well, sum or the average is the same because we just divide by n, one to get the other. Then there is like other query models. One of them that is very natural and is becoming like quite popular and also appears in good venues recently is the one where you have not necessarily a tree, but any graph. And the query is that you pick any vertex, and as an answer, you are given a path, an edge that is incident to this vertex that you query. And this edge is promised to lie on a shortest path to the target. So basically, I query V and I learn which way I should leave V to be on a shortest path to the target. But I don't know if the target is nearby or very far away. And if there is many shortest paths from V to the target, then I will get one of them. I don't know which one. So, and the next vertex I query doesn't have to be the neighbor of V. I can pick anybody anywhere in the graph. So, and on top of that, people also study like noisy models where for those who like probabilistic stuff, where you can assume, for example, that some replies will be incorrect, which is kind of related to the very, very old Rennie and Ulam problems, like 20 questions game. Like one person picks a number and the other has to guess which number was picked. And the person who picked a number can, for example, lie once or twice. And what then? Like how many queries we need? If some of the answers are incorrect. Okay, so I think that would be all. So thank you for attention. Maybe you have any questions.
Yes, thank you, Darek, for your very nice talk. Are there any questions? The audience? I don't see. And on the YouTube or Facebook? We are waiting for Julian. Okay, no questions on social media. Oh, Darek, I have to apologize to you. I was instructed that I made mistake because when we spent our holidays in the university holiday resort, you played with our children in board games.
Yeah,
yes,
that's what I thought about. That there is a story about playing board games in the forest.
They were so excited that they are playing the professor, and you were entertaining our children with board games. I remember. Sorry.
Yeah.
Okay.
But I immediately thought about it. Yes.
So we have to repeat maybe some board game session.
Yeah, board games are always good. Yes.
Yes. So, any comments, remarks, questions? Last chance.
Yeah, I have an email.
Okay,
I mean, if you will be interested later on, or maybe if you want to have a bunch of references to any of the problems, then I can send them out, of course.
Okay.
Yes,
yes,
please.
It's very good
Thank you.
opportunity. Yes, please. Okay, so I think I would like to thanks Darek, and thanks to Hannah also, to our speakers of today's sessions. And we invite you to our social media for posters and videos recorded by and created by students. Yes, Rita?
Yes.
I'm grateful for the invitation very much. By the way, how do I find this social media place? Like in the chat?
Okay. I will send you email, okay?
In the page.
In the web page.
In the page, yeah, sorry.
The web page in the main page, you can find this.
Okay, great.
Thank you. Thank you very much.
And today we have some videos and posters of Michał Polczewski, Jaworek, Laskowska, Gapiński, Zdunek, and Kurzyk. So you are welcome to visit our social media and listen to our great talks of our students. Thanks a lot, Hanna, and thanks a lot, Darek. And Rita, you would like to say something?
Yes, I'd like to just to say, okay, thank you again, and invite everybody tomorrow. Tomorrow we have 2 sessions only. The first is with Juan Carlos from Spain. And in the second session, we had the celebration of our 10th anniversary. So we hope everybody can be with us. We will have the company to our professors, all the organizers. We'd like to say thanks in a special way to our professors. All of them accept to be with us tomorrow, which is very nice that because many of them, they don't meet together. So it will be very nice for tomorrow. And then before to finish, I would like to say that maybe you see that today Magda Detlef look especially beautiful. And this is because it's his birthday. So I like to say in the name to all the organizers, happy birthday for you, Magda.
Oh, thank you, Rita.
This is very nice for the new year. So I hope you have really, again, a very good starting of a new year and enjoy this. So,
okay, thank you.
Thank you.
Rita, see you soon. To celebrate New Year together.
Yeah.
And tomorrow we will have some session, party online, yes?
Yes, we have party online. Yes, we invite everybody.
Online party.
Maybe wine with you or etc. For me, it's not possible because in our university is forgiving to have wine in the university, but of course I will have coffee to celebrate tomorrow.
Perfect.
Okay.
No
Thank you very much, everybody. Somebody like to say something?